Welcome everybody to this week's collective learning meeting. Please remember to mute your microphones unless you want to ask a question. Feel free to use the chat box. If you type a question there, I, Christine Tang, can ask the question for you. Our presenter today is Tim Clancy, a WPI PhD candidate and founder and CEO of Dialectic Simulations Consulting, LLC. Tim builds models to reduce violence and instability. And Tim worked 25 years as a consultant to Fortune 100 and government agencies and spent 2 years in Afghanistan supporting counter roadside bomb analysis and retrograde for the Department of Defense. Thank you for your service, and please feel free to ask questions at any time, but Tim prefers that you ask questions at specific stopping points. Please take it away, Tim.
Thank you, Christine. Appreciate the introduction. I always try and clarify, not a veteran, was civilian accompanying the force, so not uniform, but civilian. So hopefully the share is coming across. And first of all, welcome everyone. We've got folks from a lot of different fields, and this hopefully will be useful and interesting because I'm pulling these ideas for a little field. So I'll go through a little bit of my motivation and purpose to get started. But as for the structure of this, I've got a lot of material to cover, but with the CLM, it's often work in progress. So I'm going to go through some of the feedback I'm looking for as well. And I'm also looking for feedback if you have something to say during the meeting, or I put my ResearchGate URL. These slides will go up there. There'll be a YouTube video. So if you want to contact me with feedback, I'm really looking to flush this out and form it into a paper. But this is the first presentation of this working topic. And what we're talking about is sort of expanding the causal vocabulary. It's for the system dynamics field, which I myself am in. That's my PhD. The WPI department is system dynamics. But I think this has applicability to any complex system. So I'm hoping there's some usefulness or some interesting ideas, because this vocabulary comes from lots of different areas talking about complex systems and causation specifically in complex systems. So again, my ResearchGate is up there. These slides will go up there. If you have questions or comments, I'll have a couple prompts throughout. There's a few interactive points, but if you think of something afterwards, just feel free to contact me. So the motivation and purpose is I've completed my dissertation. I'm waiting for the defense. In the dissertation, I'm looking at violence and instability, and I'll get into a little more deep later. There was one big question gets into causal analysis. What is the root cause of violent radicalization? So this required a lot of heavy lifting on causal analysis. We had to really dig deep into what is the root cause of a complex system. And the system dynamics methods, for those of you who are joining us from other fields, system dynamics is a simulation science founded by Jay Forrester, one of the three legs of the stool: discrete event, agent-based, and system dynamics. As I went through the system dynamic methods, it seemed like the language, the vocabulary, and the techniques were inadequate. That's probably as much as reflection upon my lack of knowledge as it is the field. So part of what I'm doing today is looking for some of these things I'm going to be introducing already exist in system dynamics, but we may not describe them in the same terms. Some of them I'm saying, have you seen this before and I just missed it? Or is this really an area where we can expand the vocabulary of system dynamics and bring it in line with other complex systems analysis? When I looked into this, so in my dissertation, when I began looking at, okay, if system dynamics doesn't have a lot of discussion about causality and causal analysis beyond its basic premise, I started pulling in from physics, cosmogony, biology, complex system science, pulling from Santa Fe Complexity Institute, work that's done in astrophysics. And I began pulling together this vocabulary and this way of thinking about causation. And my purpose today is I want to introduce this vocabulary of this debate to system dynamics. Now, this is an ongoing debate. So this is something, if you're more familiar with this or you've been in the background, this discussion of top-down causation, bottom-up causation, types of causation, it's a very active, ongoing debate. And I'm not trying today to really get into the philosophy of causation or solve the debate of top-down versus bottom-up causation. I'm really trying to introduce the vocabulary and show how it fits together with some of what system dynamics is already doing, but some of the things we could be doing going forward. So the feedback I'm looking in the collective learning meetings, we always like to start for the feedback. At this point in the work in progress, I'm looking for literature suggestions of system dynamics perspectives of causal structures that go beyond CLD precedent antecedent. You know, in Sturman's book, we typically think of causality as A phenomena affects another phenomenon and causal loop. I'll go through it in sort of one of the types of causation, but I'm looking if there's other versions of this, either in system dynamics literature or systems thinking literature, that gets into this directionality, hierarchy, multiple types of causation. And if so, I'd love to incorporate it. Ideas of where to frame this article, where to publish it, always open to that. And also questions, critiques, and feedbacks on the work so far, always looking for that sort of feedback. I'm going to flash this on the screen quickly. This is simply the sources that are in this. When this goes up on YouTube, if you want to see where I'm getting this information, pause it here, write anything down you need, hit me up on ResearchGate. But these are the sources that I'll be referring to in the presentation. And to really get us started, I want a quick interactive piece for a thought experiment. So the thought experiment, and this is framed by Ellis, George Ellis, but the thought experiment is, what causes a plane to fly? So I'm going to turn it over to you, the audience, for a few short answers. Like, what are the things, when we think about causation, what causes a plane to fly? What are some ideas?
So from a physics perspective, you're creating a vacuum over the wing, and it's the vacuum that kind of sucks the plane upward, if you will.
Excellent. So there's a physics, it's the molecules, how they go over the wing. What's another cause, a different kind of cause that causes a plane to fly?
Our desire to fly.
Right.
Is a cause. So.
Passengers want to fly, so a plane's flying because passengers needed it, or cargo. Anyone else with an idea of what causes a plane to fly?
The traffic controller that allowed it to fly.
Exactly. Governmental permission. You have to file your route. You have to do it. Otherwise, you're going to get in trouble. Let's get one more that hasn't been touched on. What causes a plane to fly?
In the chat, people have said pilot and enough resources.
Exact, pilot, resources. So when we think about this, many simultaneous causes are always, this is probably one of the distinguishing characteristics of a complex system. It has many simultaneous causes that are all equally valid. So physical causes, it was mentioned, air molecules crossing over wings create lift. Local causes, like the immediate at the time, there's a pilot who's flying it, an airline scheduled it. System causes, passengers have a desire to travel, engineers designed it to fly, airlines exist to fly planes. All of these causes in the complex system of flight are all simultaneously operating. And you can begin to look at these as directions of causes. So physical causes are what we call bottom-up causes, those molecules going over the wing. You could construct the cause of flight by looking purely at the physics and saying, well, it flies because of this arrangement of physics. But you can also look at local causes, which are same level. These are the pilot flying it at the time. You can also look at system causes as being top-down causes, right? An airline company, to serve the needs of passengers and cargo, schedule the flight. The government set up a flight regulator. These causes begin to have directionality. They are bottom-up causations, same level causations, and top-down causations. And why does this matter? So the thought experiment, what causes a plane to fly? That's an interesting thought experiment. But one of the research questions in our dissertation was, what is the root cause of violent radicalization? This is a very important question, historically and contemporary. And it has all these simultaneous causes. There's not just one thing you can point to for violent radicalization. And when you're talking about using simulation science or system dynamics or even complexity science to address problems like this, real world problems, understanding the root cause amongst all this simultaneous cause, teasing that out becomes very important, because you want to direct your policies as close as possible to root causes or a collection of simultaneous causes. This becomes a very tricky problem to unparse. And this is where I found the difficulty in system dynamics, even beginning to frame this problem in a language of causality that went further beyond a causal loop diagram, antecedent, precedent, things like that. So this gets us to really the categories of causal terms that I wanted to introduce today. And we'll go through each of these in order. There's points where we want to talk and maybe get through some interaction, but there's causal terms for establishing the hierarchy. There's types of bottom-up causal mechanisms, top-down causal mechanisms, transition between the level terms. There's also some experimental terms. And this is the vocabulary I want to introduce to system dynamics if it doesn't already exist. Throughout this, I'm going to try and show how some of these things we're already doing. We're just not necessarily being explicit about it at all times. And then as we go on, The meeting's scheduled to end at noon. We do have some bonus slides where I can show how we use this causal analysis in our recently published research to conduct an experiment on that question of root cause of radicalization. But if people need to leave, that's fine. I've kind of got it marked as bonus slides, so it may go a little beyond the hour. So when we talk about a system hierarchy, we really need to have a way of organizing these. You know, if we're going to talk about directionality first, how do we build a system hierarchy? And this is pulling a lot from Ellis. You'll see the links for the names come up at the bottom, but it goes back to that sources. So Ellis talks about a hierarchical class, and it's determined by the nature of the entity in that class. So if you think about establishing a hierarchy class, you want everything in that class to be a similar entity. So here's a picture from a System Dynamics Society PhD colloquium at a conference a couple years ago. This is a class of people in an academic field or university. They are all people, right? They all share the same entity in that class. They are people. Now, above this, you may have a class of universities, where everything in that class is a university. You may have a class above that of a field where the universities contribute. But the key is within any one class, everyone is the same entity within that class. Now, within a class, there's this concept of hierarchical rank. So a hierarchical order of entities within a class that allows you to distinguish sort of their hierarchical rank within a class. And this is an example. This is the MIT org chart for senior leadership. It was an easy org chart. But now, even though these are all people and they belong to class of people in a university, you have introduced a hierarchical rank within that class that can help you sort how do we rank these entities. If this was business people, is the class in that their hierarchical rank in business might be worker, supervisor, leader, executive. You can think of these as different ways. It might not always be organizational hierarchy. It may be some other kind of hierarchy, but it's a rank within the class. Then the causal type gets into, and this is in the backup. There's a backup slide that goes through this in more detail. What specific causal type is that within this rank and class? It's getting down in the weeds for what we were doing. We didn't use that in our research, but it is out there. So when you assemble the system hierarchy, this is, again, Ellis is talking about, George Ellis is in his paper, some commentary on top-down causation in complex systems. You build the hierarchies of a complex system by arranging your class. Each lower class underlies what happens in a higher class. The people of a university as a class underlie what happens in a university as a separate class. But each class functions according to its own laws and behaviors appropriate to that class, describable only in terms of language suited to that class. This is how you begin to get a little crispness in the causal definition when you're arranging these classes. You can talk about people and behaviors and attitudes and culture, but when you get to the class of universities, you would describe it in different terms. You might have different functions, and these are social systems, but you can do these in scientific systems as well. So these are some sample causal hierarchies of systems that Ellis provided. I'm going to do a natural system and a human system just to show how you can build these classes up and create a complex system. So you begin at the lowest level, right? This is sort of the theory of everything here on the left, right? You begin with particle physics, you get level 2 is atomic physics, physical chemistry, material science. Each class has its own laws, its own science, and underlies the class above it. Earth science leads to space and solar system science. That leads to astronomy. That leads to cosmology. A human system may start at the same level. We start with particle physics, atomic physics, biochemistry, cell physics, but then we get into physiology, psychology, sociology, economics, politics. You begin to see that these classes of hierarchies can be arranged in different, for different purposes to represent different complex systems. But the key is each class underlies the one above it, but has its own language. It's consistent in that. So what we've done is, if you think about our what causes a plane to fly, we're on the right hand here. We can locate those causes, the bottom-up causes, the movement of the molecules of the rings. That's particle atomic physics, the social structure of passengers want to fly, the government that put together the flight registration. Those are beginning to get into sociology, economics, and politics. You can begin to see how all of those causes in a hierarchy are now present in this question of how our plane to fly. And for the question we approached, violent radicalization, these questions are too. What is a biological adaptation that suits us for predatory violence? What are the social pressures or social influences? What are the human causes? Those things all exist in a similar hierarchy system. And this is what we put as our system. When we did it, we created 5 classes. So at the very lowest level was a class of incidents. These are, and we scoped our scoped efforts were only looking at mass violence terrorism. We kind of put a boundary around it so we could focus on something. But at the bottom level are the terrorist incidents itself, from when a person leaves the door to undertake an incident, a terrorist act, to when that incident completes. Above that is the class of agents. Those are the people that are conducting the terrorism or might be subject to radicalization. They are individual people in this class. Above that is networks and actors. These are groups of people. So it could be a network, could be your social network, your online network, your community network. Actors could be a state actor, a non-state actor. You know, these are groups now. So in this class, we're no longer talking individuals, we're talking about groups. And you go up class of spaces. This is a concept that is very important when we deal with influences is, are you in a governed or ungoverned space? You know, are you in a space where a sovereign actor can exude lawful authority with relatively few barriers and, you know, conduct search warrants, do investigations, or are you in an ungoverned or ungovernable space where that is difficult? Now, traditionally, this would have been, you know, someplace like Afghanistan and the US, and this you can go back in time and think of this as a key part of the debates. But even with online spaces now arising, ungovernable spaces could be places like 4chan or 8chan, places that on the internet that are tricky to do those investigations, or they may be spontaneously generated ungovernable spaces within a protest site or a riot site or an area where you have a confluence of people that diminish the government's ability to investigate, even if it's for a few days or a few weeks. And there's an example going on right now in Canada. There's been other examples that go on, both left wing and right wing, where you have ungovernable spaces for short periods of time. That's the entities in this class. And at the highest level, we have the class of symbolic, abstract, and societal dynamics. So this was our causal hierarchy. We approached this problem for radicalization. We said, this is the complex system, and there's causes, and we'll go into, as we continue this example, there's causes throughout this that are acting simultaneously. There's not one cause within the system, but we first had to build our system. And does any of this sound familiar? I want to ask the system dynamicist if this sounds familiar to something in system dynamics, but then also maybe to those of you from other fields, does this sort of class hierarchy or common entities within a class sound familiar?
I'll jump in. So what I immediately think of is class hierarchies in programming, like object-oriented programming, where you have inheritance from one class to another. And what does the inheritance look like in this case? Is it assumptions, mental models? Is it something else? Or
we're going to touch on that, because that's when you're describing inheritance, we're going to talk about causation in some ways. So I think you can almost swap those words a little bit. But we'll go through, computers come up as an example that we'll get to in the types of causation. But it's in this case, the class of hierarchies is there's a causal relationship between lower and higher classes and higher to lower classes. And if that's a term, if I'm understanding inheritance right, it's that, because Ellis uses a computer as an example in his thing. He's like, there's electrons moving through transistors that are assembled in hardware that then have software and then have applications. And then you can put up these classes within even a computer where the laws of the electron are a different language than the laws of computer programming, or even types of computer programming when you're getting into object oriented. Is that kind of what you were talking about?
Possibly. I'm not suggesting a particular model, but
yeah. Any of the system dynamicists on the thing, does this class hierarchy of class of entities sound familiar?
Tim, if I might jump in.
Go ahead.
Can you go back to the previous slide? Yeah, when I look at this hierarchy and look at the first level, a class of incidents, what comes to me is really reference mode, which if complete would tell a story. These are not isolated incidents, but a set of incidents which occur in a certain sequence, and they can tell a story. So that the that is the first level of systems thinking. That's what defines our boundary and the problem. When I think of your second level, class of agents, these are subsystems, and it's a mapping of the first level into the state space. And you have a dynamic hypothesis, an aggregate upper level system conceptualized. And you go to the third level, which is class of networks and actors. To me, that is stock flow consistency.
Mhm.
Each agent in the second class is elaborated into a role system. And we have a way to map them.
Mhm.
And then the fourth level is more abstract, that there might be multiple influences, or there might be multiple manifestations of the same network, one operating in the governed space, the other operating in the ungoverned space, for example, and yet another which might have influences from both spaces out there. So this is another important aspect of it, which is multiple manifestations of the same structure, which with environmental changes can lead to different types of outcomes. The class of symbolic, abstract, and societal dynamics, this might be like having a paradigm or a theory. Like in economics, we had a theory developed at the time of Industrial Revolution, and that was the theory of market as elaborated by Adam Smith and Mills and other early economists. And then came another theory which again observed multiple incidents 100 years later, in which in fact ownership was very clearly defined. It was separated from workers, and that created another theory. So is my question is my interpretation, does it make sense to you?
It definitely makes sense. There's a different way that I was going for in this, which by the way, Khalid Saeed, my PhD advisor to everyone, he is one of the et al. In the Clancy et al. In the paper below. So, but he did not get a preview of this. This is live. So it's actually, so that's interesting. What I brought as a focus was actually Forrester's description of classes of problems, or generic, and I think this lines in very closely with what you're describing. When Forrester in 2007 listed what are the 9 things that make up a quality paper, is that it's descriptive of other members of a class of systems to which the system at hand belongs. So his description of classes and hierarchies shows how the model behavior fits other members of the class as policies followed by those other members are tested. I think this is very much in line with what you're talking about, is that in system dynamics, we have this hierarchy of both theory development, that it begins with reference mode and then moves up through it. But we also have the concept of classes of problems, that you're modeling a class of problem or generic system as opposed to a specific problem because you want to be broad. And this comes from that Forrester address of the system dynamics in 2007. But I think what you talked about was very relevant too, and we'll get into things like manifestations and things like that as we proceed down the vocabulary.
I just want to add that my interpretations usually are at the level of plumbing. That's what I learned from Forrester. Stay away from abstraction and try to interpret things in a way which is really at a very basic level of thinking and understanding. So I try to stay away personally from very abstract things. And if I encounter abstract things, I try to interpret them at a level of plumbing. I think Foster was a plumber par excellence. And I don't know. I don't know if I can get there, but I try.
Yep.
Nobody should.
Yep. And I think you'll see too, when we talk in this case, abstraction and symbolic are a plumbing related in terms of abstracted symbols and iconography and ideas as abstractions, not necessarily abstracted vague concepts. But we'll touch on when we go through the example, how we get to the plumbing of something like an abstracted concept that may influence someone to radicalize itself is not very abstract. It's a thing that you can trace and mean and put in the simulation. But in this case, we had a class there of symbolic influences that were societal dynamics.
Tim, I don't want to monopolize this discussion, but my question again, does my interpretation make sense? It's in line with your thinking, or is it different?
This is, so what you described, I think, is an adjacent perspective. This causal hierarchy is plumbing. This is trying to depict the plumbing of a system that you may be trying to simulate. So all of these things may end up being depicted in a simulation because within them, the plumbing of it, all of them share potential causations and influences on the system. And our job is to figure out, and it's not modeling the entire system, this is all scoped by a problem, but what is the true root cause? Is it coming from the top down, the symbolic, abstract societal dynamics? Is it coming from the bottom up, the terrorist incidents themselves? And in any complex system, to have a process to proceed on your plumbing, you first have to build the hierarchy of, the plumbing in the sewer. The hierarchy in the sewer might be the sewer lines, connect to the interior lines, connect to the faucet. Those show levels. So this is probably a bit more concrete. What you're describing, I take of as a development of theory as it unfolds through the progress of a work. So yours may be adjacent to this, I think, as a perspective looking at it.
Fair enough.
Yep.
Let's proceed.
Okay. So the bottom-up causal mechanics, and this is the thing I want to know, if in system dynamics, they have this way of constructing complex systems through causal vocabulary. But when we talk about bottom-up causation, what do we mean? What are some selected bottom-up causal mechanisms? And these are probably the most familiar to anyone in the hard sciences, because this has sort of been the prevailing view. There's mechanistic interactions, discrete interaction between two information entities, conservation of energy, conservation of mass, there's all these things, billiard balls, right? We think of just the interaction of two, it's mechanistic. A influences B, a force or something. It may be physics, it may not be physics, depending on the domain context, but it's a very specific, two entities interact and the interaction is very clear, it's discrete, and we can understand it at a detail level. The second kind of bottom-up causal mechanics is causal processes, which are collection of mechanistic interactions. You may not need to map every single interaction along the chain. You can infer across the chain, but it has a start and end and a result. And this is an example of this is, any student who went through the last 30 years of biology heard about mitochondria, the powerhouse of the cell. This is a causal process in biology that is understood as a collection of mechanistic interactions. And again, these are the bottom-up causation in a causal hierarchy. But there's another one, which is bottom-up emergence, which is the parts of a system interact by simple mechanisms to create complex behavior. Now, again, we're talking very physical things here at the start, but even, for example, the formation of snowflakes, how crystalline formations can create complexity by very simple interactions. So these are the types of causal mechanisms. If you're looking at how does something from lower in the causal order influence something higher in the causal hierarchy, it might be through these bottom-up causal mechanisms. And I think all of these in some ways or another are fairly well represented in system dynamics. We sort of, by virtue of a stock and flow, may be an integration of the change in a causal process over time. We're integrating that, but we are sort of reflecting cause and effect, or trying to reference, and certainly trying to understand what creates that emergence. How does that emergence come to be? Top-down causal mechanisms. This is the trickier one, and I'm not getting into debate or philosophy, but this is a controversial subject, that causations can come from the top of a system and work their way down. And there's 5 types of top-down causal mechanisms, some of which I do think we use in system dynamics. Algorithmic, right? Higher variables influence lower variables through structure, boundary conditions, and initial conditions. The gentleman who talked about computer programming, this is the example Ellis used of, you cannot determine what's going to cause, if you understand the state, electrons and transistors, you still cannot from that forecast the activities of a software application working through hardware. It's the application itself that gets loaded on that creates a top-down causation into the computer through these variables. It's setting where the transistors open and close. It's doing that through the operating system. This is an example of algorithmic top-down causation. I don't know of any good examples of that from system dynamics, but the next one should be very familiar to system dynamics because it's one of the first things we often teach, is non-adaptive information control. Higher variables influence lower variables to obtain specific goals through feedback. And this is where system dynamics is all about feedback effects. So we take the classic causal loop diagram depiction of a limits to growth where we have births and population. On the left is the feedback loop that as you have more births, you have more population. As you have more population, you have more births. The right hand is the negative feedback loop that creates the balancing loop that as you have more population, it increases deaths. Deaths reduce the population. And a non-adaptive information control is the concept of a feedback loop with an exogenous constant. In this case, food scarcity. There's a certain amount of food, and as you reach that threshold, death and exceed it, deaths will increase. And that way the system drives itself to a fixed, non-adaptive, non-changing external goal. And this is, we talk about exogenous as being outside the system, but there's a simple example of this too, thermostats, right? You set the temperature at a certain temperature goal. Now the system's going to adjust itself and get to that temperature. This is an example of a top-down mechanism, causal mechanism of one of the 5. So I think this one's already in system dynamics because we use it. A third type, adaptive selection. Many entities interact following by selection of best performing entities. The classic example is evolution, Darwinian evolution, right? Many organisms, species, individuals, depending on your unit of selection, interact. Some of those are selected for fitness, and there is an adaptive selection that builds upon itself. Now, I'm not sure if system dynamics does adaptive selection, but agent-based modeling very frequently uses sort of adaptive selection, top-down causation. And if you have a hybrid model where system dynamics is joined with agent-based, I would imagine this might come up. But I couldn't think of any truly adaptive selection in system dynamics as a standalone technique, unlike the next one, which combines adaptive information control. This mechanism is the same as non-adaptive information control, but with adaptive goals. So we go back to our, and the goal adaptation can be simple or complex. So a simple example is the feedback loop we just showed that had an exogenous fixed constant. It's an external system, it's just a number, it's fixed. Now, if we link and make that endogenous, that the level of food scarcity is driven by the population and the amount of food they consume. Now we've created an endogenous system where the food scarcity itself is adaptive to their food consumption. That goal that it's seeking to will, and you can expand this. This is a simplified view, but you could put in, food production and all those things. The character, though, is that the goal that the system is seeking is itself adaptive and changing. It's not fixed like I put a temperature in the thermostat. It itself reacts to the system. A complex version of this, if anyone does any streaming for Netflix, YouTube, even Facebook, the algorithmic sorting of our preferences. As we watch things, the system is taking an algorithmic adaptive selection. What do we prefer? Adjusting the adaptive goal of what it suggests, and we end up with cat memes or angry people talking about politics. But this sort of adaptive information control is a top-down causation that determines what does our Facebook look like? What does our Netflix look like? You take two people with two YouTube histories and they will have very different suggestions based off this sort of adaptive information control. Intelligent causation. This is the 5th cause of top-down causation that Ellis talks about. a special case of adaptive information control where individuals or groups arbitrarily select symbolic representations. And Professor Saeed, I think this is where I was getting to in terms of the use of the word abstract symbolic is not in terms of fuzzy, but the manifestation itself is as an abstraction of many, many inputs. It's distinguished from adaptive information control because it uses language and abstract symbolism. So this is really intelligent causation is the reason it's a special case is this exists in humans, and it's the way humans convey things that then have influences on the system. And, you know, the other is it's irreducible. You cannot take the manifestation of this abstraction and tie it back to any one person or thought in isolation. So you mentioned economics, right? We can describe economics as feeding many of these ideas from different contributors over time, but we can't pick it out and say, well, it's only Schumpeter, or it's only Malthus and Ricardo, it's only Smith or Marx. It's irreducible to the net amount. And of course, starting with economic, going back to the airplane experiment.
Let it saying, please.
What?
Let it saying.
What was that? I didn't understand that. Okay. Airplane designs. We go back to our thought experiment. What causes an airplane to fly? An airplane design is go ahead. Go ahead.
What I want to add was that when I mentioned economic theories, the theories draw from human behavior aspects, but they differ in their boundaries. Like I gave two examples, the theory of perfect market, which arose out of ignoring ownership. And then another theory which included ownership and ignored something else. So these theories differ, their outcomes differ because they select different system boundaries. So,
I may incorporate that. That's a really good point, because the whether it's arbitrary or not, the selection of how you represent it, you know, what are the boundaries you include or don't include, I think is very relevant. Even when we're talking about simulations, whenever we design a simulation, we pick things in the boundary, we exclude things by other boundaries, and that reflects what the simulation is going to show.
Actually, our emphasis on constructing a reference mode assures that we create a relevant boundary. We include in the model all variables which are relevant to the problem, and we exclude those which are not.
Right.
So the boundary selection is very important. And that's the reason for or emphasizing constructing the problem first. Mind you, I've seen models which start from building a model, not defining a problem, and the biggest issue with those is incorrect boundary.
So, sorry, there was a question in the chat a while ago. I didn't see it until now, and the question was, are each of the levels that you talked about before considered closed systems? And I thought we could talk about this because of closed and boundaries. Okay.
That gets tricky because closed and open systems have different definitions depending on which field you're in. I would say that they are, I think, you know, all of these classes of hierarchy are sort of useful abstractions that we as humans put on a continuum of emergence to be able to say, if I'm studying physics, my boundary is here of what I study. But obviously there's a continuum where it smoothly goes throughout as physics evolves into biology, biology evolves into chemistry, chemistry evolves into, you know, these things smoothly flow up and down in a continuum. I think the distinction of closed and open system gets into, especially when we talk about simulation modelings, what are you trying to model and what is the problem? And what are to what Professor Saeed just said, what are the relevant pieces? Are the relevant pieces inside the system that you're trying to model? And that goes to a distinction. Now, since closed and open have two different definitions depending on where you're standing, I'm not going to get into like typologizing. I might do that in the paper, like closed and open, but it becomes a quadrant. I think the key thing though is what problem you are trying to model, where you put these boundaries of classification should be driven by that problem itself. The problem of radicalization is not going to look the same as the problem of the origin of the universe in terms of where those boundaries are and what's in and outside that system. In this case, the intelligent causation, the examples I wanted to get to, for example, what causes an airplane to fly? Airplane design. And airplane design is people making choices to solve a certain problem, but it is so complex and so thing that from an airplane design, you do not determine an individual mental state of any one person who contributed to that airplane design. You understand the airplane as the airplane design is now a standalone cause, which then influences billions of dollars or hundreds of millions of dollars of manufacturing, shipping, construction, how we put it all together. But it itself is an artifact that cannot be reduced to any single input that came from within it. Even more abstract concept is the value of money. What is the value of money? Well, it is the collection and of intelligent choices by people over time, but you cannot go back and pinpoint any one person who said they determined overall concept value of money. We try and get close with the Fed and things like that, where we're trying to make articulations, but it is itself something that is its own form, that it supersedes the input of any one individual. Another concept in sociology, social construction of roles, norms, expectations. You have all these influences that people are making choices, but the intelligent causation at the point of abstraction or symbolic becomes then an influence itself back into the system from a top-down mechanism. And these are simply some of the selected top-down mechanisms. It may not be an exhaustive list either of top-down or bottom. But my question, I guess, to a broad sense with system dynamics is, are these terms of vocabulary used, top-down, bottom-up, types of causation existing in different forms? Because it would seem to have modeling influences as how you choose to model these in the thing, which is sort of why I'm hoping to introduce this discussion. So example of incorporating causal direction and modeling process, classic causal loop diagram, violent radicalization that we did. This is a synthesis of expert opinions on how does violent radicalization grow within a given set of boundaries that were relevant to the problem we had. It's a flat view. It's a top-down view. By nature of the causal loop diagram being flat, we see it as all causes are, on the same plane. But when you flip it and turn it on your side and extend it, you now have directionality where you can see some causes are bottom up, other causes are top down, some are same level, and you begin to see this causality going on of influences from different levels, all these simultaneous causes and how they're moving through the system. How this gets into the modeling process, I think, again, we already do this. I saw Kareem was on here, so Stella's going to come up as an example. We have this directional causal thing. You can easily represent that with modules. Now, that doesn't mean you're always doing it with modules, but in this case, when we built our simulation model, we literally built the incidents, the agents, the networks and actors, the system of spaces, and the system of systems to reflect these 5 levels of hierarchy and the types of influences going back and forth between them. And this is, I think, the challenge of a complex system is you can't just isolate out the terrorist incident and from it derive how violent radicalization works. You need to understand the system. So let me pause here. Any questions on bottom-up or top-down causal mechanisms? Do any of this sound familiar? Any of this? Yeah, Richardson was talking about it in 1995, or there's a paper out there by Andreas that might be 2000 or anything like that, that these terms are already in the literature for system dynamics, or would these be new terms to describe causation in a system? JJ is asking, it would be very interesting to have a simple practical application of these general ideas. That comes in the bonus round. I'll walk through that as we get there. So there is an example coming up from the research of how this might be used, how we used it to frame our problem. But I want to go through 2 more sets of terms, transition terms. These are the terms that are useful when crossing boundaries of hierarchy. So coarse-graining aggregates individual entities' interactions to evaluate a higher level of hierarchy. So we think about, like, you don't measure every single particle to determine the average temperature in a gas. You just measure the temperature. That's a coarse-graining activity where we've gone from individual mechanicistic interactions to a higher level. And there's a set of criteria. There's in the back of this Flack, who's done a lot of writing on coarse-graining and fine-graining. she indicates that you don't just do this willy-nilly. There's a reason why you do it, a value you do it, and a set of criteria of how to do it. But this coarse graining allows you to take information that may be microscopic or discrete from one level and bring it up to an entity at another level. And we do this in system dynamics. Stella, for example, very simple smooth function. One of the criteria is that you're integrating the microscopic activities to get a macroscopic value that is still true to the system. And this is what a smooth does. A smooth function in system dynamics takes some input, it does an averaging time, and it simply gives you the value of the system at that macroscopic level. When we did it for radicalization, this diagram shows on the right, when a terrorist incident happens, there's many cultural scripts that are created by media. Millions upon millions of cultural scripts that you could individually track, like particles in a gas, but coarse graining them, where we sort of consolidate them into one influence at the level, that fifth level, abstract, symbolic. What does it mean when Columbine happened? What does it mean when a mass shooting happens or a terrorist incidents? This is a coarse graining from individual cultural scripts that may be generated, pieced together to a larger system thing that it may lose information on the detail. We don't track which Twitter account or which social media or which news story created it, but it gains us information at the system level, which is how do these cultural scripts now, at once they're coarse grained, influence radicalization to certain violent ideologies. So this is one form of transition from discrete to aggregate. The reverse from aggregate to discrete is called fine graining. And this is taking a macroscopic value and creating the sort of the microscopic entities in a lower level of class. Simple example of this I found is Homer and Richardson in 2017 said, here's the influence of the field of system dynamics. They had a very high level chart that showed papers and publications over time. If you were to break that down and locate it within the broader field of science where every single book or citation of note had a place, that would be fine graining. And there's a website that does it. It does 1 million different science publications and locates them all within this massive space to say, here's the influence of any one publication. And I've zoomed in on this space where system dynamics occurs in the middle here. The red is actually Urban Dynamics by Jay Forrester. That's the location and approximate size of influence. Next to it is Thinking in Systems by Donella Meadows. And you can see at microscopic detail where all these particles relate to other things. So this is an example of fine graining, taking aggregate information and disaggregating it down to very specifics. And it's a pretty cool website if you want to go over looking at how many different areas and fields Jay Forrester was influential in. He pops up in a lot of different areas. The last set of terms is experimental terms. This gets to the question JJ had, is how do we make use of this, right? How do we put this into, we want to test and simulate in a complex system. And so the terms are, proposition is one of many simultaneous causes located. We go back to class, rank, and type. You create a table of propositions. And so in the radicalization paper, this is 4 of 16. We had 16 propositions that came from that 3-dimensional causal loop. And we list them by ID, the partial cause, the hierarchy, causal type, character of cause, and create a testable proposition. We're not saying any of these are the one. We're saying these are all potential simultaneous. If you were doing your airplane, all the ones that people mentioned would be in this table of testable propositions. Then you construct your space, your sample system hierarchy. And in this case, the example is a proposition is at a top level. If it was a bottom level, the little sphere, but it shows here in your system is a top level proposition that we want to see what is the causal influence of this in the complex system. Then you run a contingency test. And the contingency test, the range of values within which a proposition operates. Now, this is similar to sensitivity in system dynamics, but the key here is that you got to this through an explicit structural causal mechanism. You're not dancing with numbers or just randomly picking one and doing a brute force search to understand sensitivity. There is a causal reason why you are testing this proposition and these range of values. And that should be structurally, I mean, it could be abstract, it could be 0 to 1. But there's a reason why you're doing it. It's not just doing sensitivity for sensitivity's sakes. It's selecting ones based off their proposition and testing plausible ranges of contingency to figure out how it operates in the system. And when you do that, you have now this proposition has a value. Let's say it's 22. It could be 1 billion, it could be 5. But it's now got a range of values within which will then create a downward channel. And the channel is the upward or downward niche created by the contingent values of one or more propositions. So now we have the proposition at a top level had a contingent value. It creates a space downward through the system, the causal system, within which manifestations can emerge. And this gets to when someone is talking about manifestations, it gets into this, right? Well, first of all, when we talk about channels, we're borrowing here the Goldilocks zones that astronomers use. They say, look, if the proposition is you need a certain temperature of planet to sustain human life, the contingent values are too hot to too cold. Between those contingent values, you create a Goldilocks zone within which planets are likely to exist. And they use this to look for carbon-based life elsewhere in the universe. So in astronomy, they call it the Goldilocks zone. In biology, they might call it an evolutionary niche space, right? There's a certain environmental conditions that create a channel or a niche within certain species will thrive and other ones will not. So it's introducing this concept of channeling or niches or Goldilocks zone in a system paradigm to understand where within all these things may potential manifestations emerge given the contingent values of the proposition. The manifestation is simply a discrete instantiation of one phenomenon among a class of phenomena within a contingent channel. So we have here, once you create that downward contingent channel, you may have certain manifestations within it that align to that channel and that proposition. And this is an example, again, of top down. If it was bottom up, it'd be a channel going from the bottom up. But it locates these manifestations, these phenomena within your class of phenomena and says, this exists only within this channel, or these are the types of things. Now in simulation, a manifestation might be a simulation run. You can only get to this. This is representative of a single simulation run, but it should be tieable back. This is a reference mode. This manifestation of reference mode can only occur within a certain proposition or set of propositions and contingent values. It gives you a way to sort of create experiments now to say, what are the contingent values under which this proposition in combination with other propositions operate to create certain manifestations of interest? And this is where I pause. We do have the bonus round where I go into the actual example of how we did this in radicalization. I know people might need to leave it at noon. Any comments before we go to the bonus round, or are people interested in staying for a little bit, seeing this in practice, and then having comments or questions?
Can I ask a question?
Sure.
Yeah, apologies. I had a call just at the beginning, so I missed the outset. Have we covered Markov chains and Markov blankets?
Markov chains is as a form of causal mechanic, like a causal mechanism. We did cover. Were you here for bottom-up mechanisms?
Yeah. So
okay. And is that and this is where I'm asking, because maybe Markov chains needs to be added. Is Markov chains a way of examining mechanicistic or causal processes, or is it a different type of causation entirely?
Yeah, they're meant to. That's exactly what they're aimed for. Have you come across Joshua Pearl and the Power of Why? Is his book? He's the causal revolution, as he describes it.
Sounds like a book I need to read to include. I'm pulling in from all fields, so I haven't come across him yet, but he's going to be on my list to read of the Markov chains as a type of causal mechanism. Would that be a bottom up or a top down causal mechanism?
Well, I think he goes through the mechanism of how you can establish causation and how you can pick apart correlation and causation. So he's got.
Let me ask this in a different way again. Is his a method of identifying causation, and Markov chain is a method, much like we might use system dynamics as a method, or is he saying that the Markov chain itself is the causation?
No, it's the method.
Got it. Okay. Okay.
It's the method.
Okay.
It's the way. It's the way in which to analyze. I came to it through Professor Carl Friston, who does the inventor of the free energy principle. He's the world's leading or the most cited neuroscientist, who's also come up with dynamic causal modeling. So that should fit very well within the framework within which you're trying to achieve, as he describes it, model evidence. So how do you work out you create a generative model? It seems perfect for the system dynamic community. So you test competing causal hypothesis, and then your fitness, the best fit in terms of the model evidence, are the ones that allow you to identify the most likely causal explanation. So they're two I'd certainly think you should,
Excellent.
Joshua Pearl is the doyen. So I definitely.
I'll take a look at that. Thank you. I see Bruce, you're raising your hand.
Thank you. Yes, just asking about the meaning of these channels you were talking about. Is that something like a restricted context or scope?
It might be
only include certain aspects or certain variables or certain scale.
It's a restricted scope, but I want to be careful here because that term's not familiar. The way I conceive it, and I'll show in this example, is when you're talking about top-down cause. Well, let's talk about an example that Ellis used, right? The color of the fur of bear, right? Bears are all over, they're in different environments, but the coloration of their fur is caused by a top-down causal channel that if you're in an Arctic environment where white is prevalent, it's going to favor white fur. And within that channel space, bears with white fur will be favored. Whereas if you're in a more tree-based environment or hills, brown might be favored, and brown fur would then be more likely to emerge in that channel. It sets the contingencies upon which manifestations might be selected for preference or might even possibly exist. And we'll show in the example here in the violent radicalization what that means. Does that match with what you're describing or something different? You're on mute. You're on mute. You're on mute, Bruce. There you go. Oh.
Sorry, I think the answer was yes, but language is very difficult.
Well, and that's one of the reasons I want to introduce this. Is what has always fascinated with me with system dynamics is it provide a vocabulary, a grammar, and a syntax for describing systems. It's not the only language out there, but it's a very useful. So I look at this as, are these words and terms and constants useful for bringing into the vocabulary so that we can create methods, or maybe there's already methods out there that imply these and enrich them. But let me go through an example to show how this works with a real life research process. You know, our problem was determining the root cause of radicalization. And the way this problem comes about is there's an example of phenomenon, which is when individuals self-radicalize themselves in small groups of people under domestic conditions. And that is one theorist, a terrorism specialist named Sageman, that looked at swarm. He called this phenomena a swarm. He says, all you need to know to understand radicalization is what's going on in the local environment, these individuals, their network connections, and that will tell you who's going to be, and I'm simplifying. So if Sageman sees this, please don't send me an angry note, right? This is the swarm theory, but this is contrasted by a different observation made by Hoffman that is called the fisherman theory. And Hoffman's theory is that, no, it's not local groups, it's non-state actors, organized, hierarchical non-state actors that go into an environment, they provide propaganda material, they recruit, and they are causing the radicalization. They describe the debate between, or someone described the debate between them as the true root causes of radicalization. Is it swarm or fishermen? So when we approach this problem, we looked at it through this causal hierarchical mechanism, and we began with a single proposition, right? The size of the at-risk population within a given area that might be radicalized. And there's what might be radicalized is a whole nother 45-minute discussion of the permutations and the contingencies that make someone susceptible. But just for now, for sake of discussion, there's a domestic size of the at-risk population. And under a given contingency, what we found is the downward channel that created excluded fisherman-style terror contagions from occurring. It only included within its channel swarm. And this was a single proposition test. And as I said, we had 16. So this was just one insight. We said, okay, well, that's odd. Does that mean fisherman doesn't exist? Did he get it wrong? Well, when we added a second proposition, the presence of non-state actor influence. Once that proposition was added, manifestations that wouldn't fit within based on the size of the domestic population suddenly began to emerge because they were being supported by outside. Now, if you think of this like an evolutionary niche, it means if you have a lot of people susceptible to, say, white supremacy or ultranationalism or some very common thing with a large domestic population, you don't need outside actors. You have everything you need in the local space to create radicalization. But if you're in a small at-risk population, say Muslim in America or Britain, you know, the Salifi Takfiri phenomenon, that's a small enough population that you're going to need an outside influence. And therefore, the things we see emerge that have a fitness level will always be associated with a non-state external actor because that outside influence is necessary. Now, what that means was a very interesting revelation to us, is that the alternate hypothesis that the cause of radicalization is found at these top level propositions and their contingent values. This is what drives the system, is these propositions and contingent values. And swarm and fishermen are just manifestations within a given set of contingent channels. It shifted the debate from is the root cause swarm or fishermen to being swarm and fishermen are just byproducts of the system. They are not the cause of the system. The cause occurs under this combination. Now, there were 6 propositions we found working in concert. We've only displayed 2, but the hypothesis of the terror contagion hypothesis, which is in this paper, is that a top-down causation in a system of violent radicalization creates the conditions under which you may see swarm, or you may see fishermen, and you may see both. And when these two began studying it, what they were doing was not realizing the contingent values of the channels they were looking at. They were just looking at, is this influenced by a non-state actor or not? And they could find examples of both, but until you map those contingent channels, you're not going to be able to show why it is that you might see some and not the other. And we were able to test this with simulations. We ran an experiment, and this is from the paper itself. These are the 6 propositions. And everything else being equal, we only changed 2 things for the experiment. The at-risk population, it was normally 600 people. We reduced it to half size. So in the middle column here, these are contingencies to create a swarm channel. On the right is contingencies to create a fisherman channel. I see your question, Bruce. Let me just finish this and I'll get to you. We only changed the population size by dividing it in half. And then the non-state actor capacity under the fishermen, we had one that wasn't or one that was with a non-state support. And the results of this experiment is it's a channel experiment. And the results in the swarm channel contagion, if you go to the right here, there's the total attempted incidents, the failed incidents. These are things that are unknown in the system. What you know is the completed incidents. That's the stuff that makes the news, right? That's the stuff that gets the headlines. These are the completed incidents. And over a 10 to 20 year period, your total incidents in the swarm channel will be 234. In a fisherman channel with a population half the size and no non-state actors, it was only 60. So it kind of disappears off the radar because it's not as at the same severity or strength. But if you add that non-state actor influence, it goes up to 224, very close to the fishermen. Now, this is a synthetic experiment. It's using an exploratory model, but our hypothesis is they were looking at populations, Muslims in the America or United States, UK, parts of Western Europe, where the Muslim population is so small, the only violent radicalization you would see would be that aided by a foreign non-state actor versus something like I mentioned, white supremacy, ultranationalism, other forms of mass movement that there is school shootings. A large domestic population doesn't need any outside influence because it's got everything it needs inside. And this led us to this conclusion that swarm versus fishermen was the wrong question. It was, what is the system of violent radicalization and how do those propositions act on it from the top down? So I saw, Bruce, you had a follow-up question, and then I'll pause for more questions because this is the real life example, I think, that JJ, no questions, Bruce. Okay.
There are some questions in the chat. So there was a question, a channel is then a mechanism that enables certain behaviors?
Yeah, I can think of it. I think of it as a channel, and this is where we're starting to push the boundaries of what's been discussed in the terms in other literature. But a channel is this niche or this space that, if you're talking top-down causation, extends downward through the system, and certain things will be favored within that channel. Certain things may only be able to exist in that channel. They may only arise within that given set of contingencies. So it is sort of the downward movement through the system of a causation structure that allows certain manifestations, but it can be understood through the contingent values of the proposition at the higher or lower levels, depending on what direction it's going. Does that answer the question?
I just want to add that there is a parallel to what I some time ago described as the two opposing economic theories. These two scientists looked at different pieces of evidence and constructed a theory. So their model boundaries were different. So at the very top level, they were looking at different pieces of evidence. Let me just, I just want to.
I think that's important though, because it's actually, I was remembering that paper when I stumbled upon this, and the fact of the slicing complex problems. I don't reference it in here, but it's a great article if anyone wants to look at it. Talks about your time slices, how long of a data are you collecting? If you collect too narrow a slice, you may only be seeing some of these manifestations, where to build a proper reference mode, you need to abstract many time slices from and maybe, you know, use the slices themselves to create them. And I think it was from that paper that different economists had different time periods of evidence they were looking at. And, you know, as they expanded the evidence, they got richer and richer things. I think here they were looking at too few cases and drawing these conclusions from arbitrarily narrow boundary selections. Christine, more questions?
Yes, and I put a link to the YouTube video of Professor Saeed talking about slicing complex problems in our back to school sessions that we haven't had it in a while because you just watched the recording. Okay, there was another one. Hold on, I have to scroll up. Can all this be quantified as is done in system dynamics, or is it more related to non-quantified methods like systems thinking?
So I quantified this. The article that this cites in 2021 is a quantified exploratory model. So, and I don't doubt that it could go to a calibrated model. So everything in it has a numerical value, but because it's exploratory, we use certain things like how far does media reach in a population? We did it 0 to 1. At 1, it reaches everyone in the population. At 0, it reaches no one. That was a modeling convenience for the exploratory because we're in a new space here, but it is numeric. It's a quantified numeric thing that is then computationally. So these results here are not, they're not just systems thinking. I think part of the reason I want to introduce this vocabulary is I think this could extend to the language of systems thinking in the same way that we can take a causal loop diagram and use that as an outline to construct a simulation model, or take an insight from a simulation model and build a causal loop diagram to help explain it. I think this vocabulary can enrich systems thinking in the same way that it gives you a qualitative language to describe things that probably is good enough for many things. But if you have a really serious problem, if there's lots of permutations, if there's lots of resources at risk, you might want to computationally simulate it, and then you can extend naturally from this qualitative systems thinking into a quantitative. But I do think the language and descriptor is useful for both.
So this is a language and a framework for thinking about complex problems.
Yeah, so the subsequent work, I'm just introducing the vocabulary here, but there was a method we used throughout the dissertation of conducting causal analysis in complex systems that builds upon this proposition contingency testing. That is probably a work down the road. First is to introduce the vocabulary, see if there's resonance. They say, no, we already do that over here. Try and get these terms in discussion and see what that generates, and listen back to the feedback on that.
I would like to add a comment on system thinking. I think the term is somewhat underestimated. It's not a watered down version of system dynamics. Actually, system dynamics, according to what Forrester practiced, was systems thinking. And his suggestion was that there are something like 20 or so canonical forms. These are policy models, which can explain about 90% of the problems that we face. He said it many times in many occasions. And he did not pay a huge attention to what we call calibration, because forecasting, replicating history was never an issue there. So what I'd like to say is that a causal map that we call systems thinking is inadequate in terms of explaining the contingencies of the behavior. So 2 coupled feedback loops, 3 coupled feedback loops what we explain is there is our mental model. We have not tested the contingencies which might arise from those loops operating in different environments under different sets of parameters. So I personally, I do not like to separate systems thinking, system dynamics. They are intertwined. Systems thinking is a higher form of system dynamics, not really a watered down version.
Great comments. And in the dissertation, we use both simultaneously, systems thinking and system dynamics. The two problems we're studying is violent radicalization among individuals and non-state actors in insurgencies and things like ISIS. And I think having that language to describe using both was very, very effective in that. Other questions, Christine?
I don't think there are any more.
Yep. I did see one comment about application of these ideas. So the application, I didn't go over it here. One half of the dissertation has to do with non-state actor, and we use the ISIS case. That was built in 2014 to 2016. It was used by the DoD. It was applied, and that's a great example where we had a causal loop diagram that then allowed us to work on the simulation model that allowed a lot of policy forecasting and showing that certain momentum policies or popular policies wouldn't be effective, which ones. It allowed us to propose novel policies, some of which ended up getting used. But then the training from that, how do you conduct a counterinsurgency against something like ISIS, then got distilled back down into systems thinking, not in a watered down way, but in a graspable way, so that military leaders could understand these dynamics of feedback and effects without having to learn the entire simulation model itself. So we transfer between the two. We go back and forth fluidly for both. And I think a lot of it gets down to what problem are you trying to solve? What's your audience? What's their need? And I'll copy on with what Professor Saeed said, that I find systems thinking incredibly powerful to use. It's just a question of how many different contingencies or computations do you need to be able to crunch? Other questions or closing comments or thoughts?
Yes, there was another question I forgot to
Sure.
ask. Will you be sharing these slides?
So these slides, let me go back up. I'll show it at the end. Here, let me show. I may have to get back to the beginning here. So
I mean, the main presentation.
On the YouTube, this is on YouTube. It will be on ResearchGate. There's a ResearchGate. Here we go. I don't know if I'm sharing. Is it still showing the front page now?
Yes.
Okay, so the front page, here is the ResearchGate. These slides will be up on ResearchGate. There are some backup slides, which there was some commentary by Flack on the criteria of what makes a good coarse graining. There was some additional commentary on causal types from Ellis. I didn't want to jam those in the presentation, but they are in the backup slides. And all of these slides, I'll be putting this up on ResearchGate after this. And if you have a question, feel free to hit me up on ResearchGate there. That's where all my work is at.
Good job, Tim.
All right. Thank you, everyone, for participation.
Thank you.
Thank you for attending. Thank you for presenting. And for those who aren't aware, we have weekly meetings, except we won't have one next week because it's WPI break, and usually our meetings are open to the public.
Thanks for organizing this, Christine. Really appreciate it.
Thank you.
Go ahead, stop the recording and